welcome everyone. As you know, we are advertising this lunch now CFA-wide, and it seems like it's well attended, so that's why it takes a little longer for everyone to get in. Obviously, the science is getting better with time, so that's another reason. And the other thing I wanted to mention is that, as you can see, a student is sitting next to me. Actually, she's my student, and Anna Paten, and she was willing to sit next to me. For some reason, people were just migrating far away, and nobody was sitting here. So I just wanted to show this as a proof, that, because she told me that there is a rumor that the students are not allowed to sit in this table. So that rumor is obviously wrong. We have an example here. And we just came from the ITC colloquium, where we had an excellent talk by Holger Baumgardt sitting over there, and he will tell us some more in a few minutes. Today we'll start with Leslie Rogers, that will be giving the CFA colloquium later today. So this will be advertisement for her later colloquium at 4 p.m. We all look forward to that. She's visiting from Berkeley, and she will talk about using MESA to simulate the hydrogen-helium envelopes surrounding low-mass planets. After her, we'll hear from Holger, that came from down under, right? That's the way to say it, from the University of Queensland in Australia, and he will discuss probing the low-mass end of the supermassive black hole mass finding. After that, we'll hear from Mark Dijkstra, that used to be a postdoc in our corridor, as many of you remember. He's currently a professor at the Institute of Theoretical Astrophysics in Oslo. And he will tell us about 3-centimeter fine structure masers, an observational signature of the direct collapse black hole scenario. And finally, we'll hear from Max Moe, that used to be a graduate student of Alabama not so long ago, and is currently in Arizona. And he will tell us about the formation, environments, and evolution of massive binaries. Leslie.
Okay. Thank you. I'm delighted to be here. Can you all hear me okay? Yes. Okay, great. So this afternoon I'll be speaking about a project that I've been working on with Howard Chen, who's an undergrad student at BU. One of the biggest surprises to come out of the Kepler Transiting Exoplanet Survey was the discovery of very low-mass, low-density planets. So these are planets with masses of just a few times that of the Earth, and yet radii and densities that demand the presence of a hydrogen-dominated envelope. To date, the theoretical interpretation of these planets has really relied on application of closed source planet interior structure and evolution codes. And on this slide, I'm just showing kind of a montage of a few examples of those. So it would be wonderful to have an open source code that's available for the entire community to use in simulating the evolution and behavior of these low-mass planets with hydrogen-helium envelopes. So the stellar evolution community is already moving in this open-source direction with MESA, the Modules for Experiments in Stellar Astrophysics. And I'm sure many of you in this room are very aware of this code. It's a state-of-the-art, modular, open-source suite for stellar evolution. And so anyone can go on the website and download it for use in their research or in their classes. And MESA, if you go and download it, out of the box, it already has some capabilities to simulate planets. So here I'm showing actually a plot from the second MESA instrument paper. And this is a mass radius diagram. And these solid red curves are showing mass radius relationships for Jovian gas giant planets, evolving as a function of age. So this is log age from 1 million up to 10 billion years. And there have also been a number of papers applying MESA to planets. But of course, the default options available in MESA are pretty much applicable, mostly applicable to these gas giant planets. So with Howard, kind of the goal that we set out to do was essentially to implement in MESA the nominal physics, the nominal inputs and physical assumptions that have been applied in these low-mass planet closed source, planet interior structure and evolution codes into MESA. So let me just summarize briefly some of the adaptations that we've implemented. So out of the box, MESA already has some capabilities to add an inert core to a planet, so you can adjust essentially the interior boundary condition of your stellar model to an arbitrary mass and radius. And then there are also atmospheric boundary conditions that are appropriate for Jovian planets that are irradiated by their host stars. So some of the updates that Howard and I did was first to connect the core mass-radius relationships to how we know rocky and icy material behave at high pressures and temperatures. So essentially tying the core mass-radius relationship to the physical properties we'd expect for rocky or rocky ice cores. We also allow for an evolving luminosity of the core, accounting for essentially the thermal inertia of a planet's heavy element interior, as well as luminosity due to decay of radionuclides in the planet interior. We've also had to adjust the atmospheric boundary condition a bit just to account for, especially for these very low mass puffball planets, their radius can change quite a bit over the course of their lifetime as they cool and contract. And as a result of that changing surface gravity, actually the pressure at optical depth 1 changes significantly. So we've made some updates to take that into account. We've also implemented just a standard energy limited and radiation recombination limited mass loss prescriptions following Ruth Marie Clay et al. 2009. And finally, we've outlined kind of a standard recipe for how to create initial starting models to evolve over time. So ultimately, we're able to simulate the evolution of hydrogen-helium envelopes surrounding planets down to Earth masses. So here I'm showing mass-radius relations calculated using MESA. And in this case, I'm not including any atmospheric escape. And these are for different mass fractions in the hydrogen-helium envelope surrounding rocky cores. And this is for planets that are 10 gigayears old, receiving about 100 times the irradiation flux that we're receiving here on Earth. And so I find this rather incredible and a testament to the power of the MESA code, that even though this code that was developed with solar mass scale bodies in mind, is able to simulate the behavior of envelopes that are a fraction of an Earth mass around Earth mass cores. Now, simulating the mass loss evolution, we can also map not just the mass radius measurements observed today to the current compositions of planets, but also to estimates of the initial compositions from which planets formed after planet formation. And so we're showing an example of this here. So in this mass radius diagram, the solid curves are for these planets that are now 1 gigayear old at 0.08 AU. The solid curves are mass radius relationships at constant final or like current composition at an age of 1 gigayear, whereas the dashed curves show lines of constant initial composition, with, again, the color scale outlined here. And so, as you can see, as expected, and as has been seen in previous work, of course, the low-mass planets are far more subject to atmospheric escape. And finally, we can apply this to explore what the influence of planet mass loss is on the overall planet population. And so to do this, Howard sampled from planet mass and initial composition space, and just to isolate the effects of planet evolution in sculpting the properties of planets observed today, we initially took essentially just a flat distribution in log hydrogen-helium mass fraction and log planet mass. And here we were considering initial envelope mass fractions from 0.1% up to essentially 100% hydrogen-helium planets. And then sampling from these initial conditions and evolving the planets at for 4.5 gigayears, we could explore how the mass loss evolution would impact the observed planet population. And so here's what we find, where the color scale and contours are just providing an estimate of the density of planets in the simulated population that ended up with a final composition and mass in this range. And so we can see, as we move to higher planet masses and higher envelope mass fractions, as expected, those planets are less subject to, or less strongly influenced by mass loss. Then here, at the low mass but high envelope mass fraction regime, actually these initial conditions are physically implausible to start out with. They're physically unbound. Then low mass planets with low envelope mass fractions quickly lose their envelopes, as seen as by this underdensity here. And then also, as you move up to higher envelope mass fractions surrounding low mass planets, the increase in radius due to the higher hydrogen-helium mass fraction leads to a higher cross-section to the ionizing radiation, and again, a decreasing mass loss timescale. So in the end, we end up where the envelope mass loss timescale is maximized at around 1 to 5% hydrogen-helium. And this roughly coincides with the peak in the hydrogen-helium mass fraction inferred by Wolfgang and Lopez. So I'll just close by saying, once the paper is published, these updates to the MESA stellar evolution code will be publicly available online for anyone to use to simulate low mass planets. And so we hope that these implementations will essentially be a springboard for many future studies into the behavior of these low mass, low density planets. Thank you. Yes, yes, and that's an excellent point. So at this stage, we're really still borrowing the assumptions that might not necessarily apply down to these low masses, that essentially treating the core as a sphere with an effective heat capacity and with a temperature that's completely tied to the temperature at the base of the envelope. So we're making the assumption that the luminosity from decay of radionuclides, there's no impediment to its transport out into the base of the envelope. And we're also neglecting any potential thermal boundary layers at the core envelope interface. But you're quite right. There's still work to be done in adding more physical realism into the simulations of the heavy element interior. And so that's one of the next steps in this research.
Question over there, and then
can you change the incident radiation that's coming on the planet, or you are just putting it to M star?
So you're saying change with time for a particular planet simulation, or can we adjust that parameter?
Spectral distribution, change with time, all these things.
Okay. So we have not implemented either of those effects currently, but in principle, I think they could readily be done. So in MESA, you should be able to adjust essentially the level of incident flux, incident on the planet, as a function of time as the planet and star evolve. We didn't do that in any of the simulations that I showed today. In order to better account for the spectral distribution of irradiation from the host star, that would involve having a separate kind of grid of planet atmospheric models to couple to the MESA simulations, which we also haven't done yet. These are all semi-gray atmospheric boundary conditions, but in principle, MESA is very extendable and that should be possible.
To what extent are you vulnerable to not knowing the equations of state or underlying physical properties of material?
Okay. So for these low mass planets, where really for these low mass, low density planets, much of the volume of the planet, even though it only accounts for 1% or less of the planet's mass, a lot of the volume is dominated by the hydrogen and helium. And so in this case, for these low mass planets, we're not even encountering the situation where the base of the planet envelope is at high enough pressures that some uncertainties regarding the hydrogen-helium equation of state that apply to the interpretation of Jupiter, for instance, really come into effect. And then the core mass-radius relationship has a subdominant role in setting the total mass-radius relationship of the planet. So questions about the transport properties of the core material and the equation and mixing properties and equations of state will have an effect, a minor effect in modeling, in moving forward, trying to develop more physical models for the thermal evolution of the heavy element interior. But in terms of the mass-radius relationships, it shouldn't, for these hydrogen-helium dominated planet volumes, it shouldn't have a major effect.
Thank you very much.
Thanks.
Okay, works. Yeah, welcome everybody. So my name is Holger Baumgardt from the University of Queensland, and today I would like to talk about probing the low mass end of the supermassive black hole mass function. Yeah, and at the start of my talk, I would just like to remind you again, as most of you know, I mean, in the last 15 years or so, we have seen a large population of supermassive black holes being detected in the centers of galaxies. And nowadays, we also know that the masses of these supermassive black holes do show various correlations with the properties of the galaxy itself. So, for example, one correlation is shown in this plot here. I mean, this is the famous M-sigma relation. Now, currently, what we have is we have relatively good black hole mass determinations in galaxies which have velocity dispersions maybe ranking from 60 to 350 kilometers per second. So that's the majority of the big massive galaxies. However, what we do not have is any idea of how this M-sigma relation actually continues, either towards more massive galaxies and especially also to less massive galaxies, and therefore also less massive black hole masses. But on the other hand, understanding how this relation continues is really important. First of all, most black holes are actually, or most galaxies are relatively low mass systems, so we might expect that actually most black holes are in this range here, and we have not yet been able to find them. And secondly, also learning more about low mass black holes might actually give us some information how these black holes have actually grown and have formed and have actually acquired their masses. So it's really highly desirable to learn more about what's going on in this range here. Yeah, okay, and then the question is, so where should we look for these black holes? So what I've shown in this plot here is basically I have taken all kinds of stellar systems that we know, galaxies, globular clusters, open clusters, and put them into a plot which shows the luminosity and therefore the mass on the system here and the radius of the system here. If you do that, you basically end up with a plot like that. So we have here in the lower left corner, so low mass and low size systems, the ordinary star clusters. Up here are dwarf spheroidal galaxies. And when we come to the upper right-hand corner, so very massive, very extended systems, we have the ordinary galaxies. So we know about black holes only in this corner up here. Otherwise, we know nothing. Yeah. Okay. So one thing that I have been interested in recent years is to study so-called ultra-compact dwarf galaxies. So what are ultra-compact dwarf galaxies? Well, basically, ultra-compact dwarf galaxies are galaxies which do occupy this range here. So they have typical masses of something like 10 to the 7 to 10 to the 8 solar masses, and they have typical radii of something maybe between a few tenths of a parsec up to something like 100 parsec. So these ultra-compact dwarf galaxies, they basically occupy a region in parameter space which is in between the classical star clusters and the galaxies. So at the moment, one has to say we really do not know where these ultra-compact dwarf galaxies are actually coming from. So there are various ideas in the literature. So one idea is, okay, maybe these ultra-compact dwarf galaxies are directly related to globular clusters. So there might actually only be the high mass end of the globular cluster mass function. I mean, that is possible. But actually there's also another idea, and that is that these ultra-compact dwarf galaxies form by the tidal stripping of more massive galaxies. So what is happening is, I mean, you take a galaxy from up here, so up to Milky Way size, or maybe slightly less. This galaxy falls into a galaxy cluster. It has a close encounter with a major galaxy, and then is tidally disrupted by the strong tidal forces from that major galaxy. If that is happening, I mean, that way you are going to remove the dark matter and most of the stars. But observationally, actually most of the major galaxies up here, they contain nuclei. These nuclei are massive and they're very dense. And that means these nuclei can easily survive the tidal forces from that major galaxy. They're going to get released in this encounter. And once they are set free and orbit the galaxy cluster, then actually you end up with a stellar system which has exactly the parameters of such a UCD. So that's a really entirely possible formation mechanism of these UCDs. And actually, I mean, this formation mechanism did gain a lot of credibility last year when Zed et al. Were able to find a supermassive black hole in one UCD. So that UCD is called M60 UCD1. And you can find an image up here. It sits next to the major galaxy M60. You can see observations of the velocity dispersion profile here, So the velocity dispersion profile is strongly rising in the center. And if you model that, you find you can only explain this central rise by a supermassive black hole, which has something like a few times 10 to the 7 solar masses. And that means about 10 or 15% of the UCD mass itself. So it's a really massive black hole sitting in that UCD. And at the moment, I mean, the only way we can explain this UCD is really the idea informed by tidal stripping. Yeah, so this UCD or this black hole, I mean, if you look at the mass, okay, this is still comparable to the masses of the black holes that we find in major galaxies. So it's not directly probing the low mass end of the black hole mass function. But again, if you now go back to the tidal stripping mechanism that we explained, or that I explained just before, okay, these UCDs, they might form by tidal stripping of galaxies up here. But one question which immediately arises then is, so what about lower mass galaxies? So because if galaxies up here can be tidally stripped, then you would also expect that lower mass galaxies, they should be even more easy to strip. And therefore, if their nuclei are released, you will end up something which is actually in the globular cluster regime. So the discovery of one black hole in a UCD actually also makes it very plausible that there should be a fraction of globular clusters which really have not formed by ordinary star formation from giant molecular clouds, which maybe most of them have formed, but actually these should be the remnant nuclei of stripped galaxies. And then the question is, so how can we find these globular clusters which actually come from galaxies? And do these globular clusters also contain black holes? Yeah, okay, that's basically what I want to talk about. So, I mean, where can we find the globular clusters? Well, actually, we do not have to go very far. Because if we look in the Milky Way, the most massive globular cluster in the Milky Way is Omega Cen. And Omega Cen has actually already since a long time been speculated to be the remnant nucleus of a dwarf galaxy. So there are really a number of observational facts which hint to this. So one thing is, for example, that if you look at the stars in Omega Cen, you take their metallicity. I mean, the stars in Omega Cen show a significant metallicity spread of more than 1 Dix. And this is highly unusual because, I mean, looking at other globular clusters, you do not find that. I mean, all other globular clusters, they really have, all stars have only just 1 metallicity. But the metallicity spread is actually what you would expect in a galactic nucleus where gas has fallen in at different times and formed stars. And in addition to that, I mean, Omega Cen, the stars in Omega Cen also show an age spread. So Omega Cen might really be the nucleus of a dwarf galaxy. Yeah, and then the question is, so does it also contain a massive black hole? Well, actually here, the observations are not 100% clear. And one big problem with Omega Cen is something that you can immediately already see in this figure here. Omega Cen has a very large, nearly constant density core. So if you plot the surface density profile, it's flat out to a very large radius. And the problem that that creates is that you actually cannot pinpoint the center very accurately. And without knowing where the center is, I mean, you cannot find the black hole. Yeah, and that is something which is shown in these plots here. So, I mean, these are observations coming from Noyola et al. So, they have tried different center positions which have been suggested in the literature. In general, what they find is there is an increase of the velocity dispersion towards that center, which they thought, okay, it points to a black hole of something like 40,000 solar masses, depending on which center you choose. But unfortunately, there have also been measurements of the proper motion velocity dispersion profile by Andersen and van der Mare, also back in 2010. And I mean, unfortunately, these proper motions do not show any central rise of the velocity dispersion, or not, at least not a very strong rise. I mean, the rise that they find would still be compatible with a no black hole solution. And so, I mean, that is currently a really big problem Normally we would expect that omega Cen should contain a massive black hole, but so far we really do not have any strong indication for it. And so that might mean we really need to push further, get deeper radial velocity measurements or more accurate proper motions, and then see what we are going to find. Okay, and so since my time is up, I will stop here. Thank you for your attention.
Often a black core is a result of the merger. We see that, that's one interpretation. When you have two black holes coming together, the core is flattened.
In galaxies, yes. Yeah.
So it's quite possible that a merger was responsible for the core in this galaxy, and then the black hole was rejected.
Possibly, if you had a merger between two nuclei also which already contained black holes. I could imagine you could also get a merger if you just have a nuclei with one black hole and then a globular cluster comes in. And that could also start to flatten out the core. But in which case you would still retain the black hole. Yeah.
Questions? Looks like everything was clear.
Seems like.
Thank you very much.
Yeah, okay.
Can you hear me? Good. Okay, first I would like to thank Avi and the ITC in general for their kind hospitality for hosting me this week. It's really a pleasure to be here. I'll talk today about 3 centimeter masers as an observational signature of the direct collapse black hole scenario. The question mark was because I was not entirely convinced about this myself yet. This is ongoing work, but I start to become more convinced that maybe I can remove this. This is work done in collaboration with Shiv Sethi. So first let me explain these fine structure lines, what they are. This is schematically the energy diagram of atomic hydrogen. Ground state is the 1s level. Then we have the first excited state 2s and 2p. The Lyman alpha line connects the 1s to the 2p transition. Now the spin-orbit coupling inside the hydrogen atom splits the NS2 level into these 2 fine structure lines. And specifically, one of the 2p levels lies above the 2s level. And the energy difference between the upper 2p level and the 2s level corresponds to a wavelength of 3 centimeters. Now, it's been well known that the 2p level especially can be populated via absorption of Lyman alpha photons. Lyman alpha can only populate the 2p level and not the 2s level. And under certain conditions, it is possible for the 2p level to become overpopulated compared to 2s. So that means that there's more hydrogen in the 2p state than in the 2s state. And if you have a larger population in the excited state of a certain transition, you can get a maser, an astrophysical maser. Now this has been known for a long time. This was speculated upon in 1960 by Potash, and there was a paper by Field and Partridge that was specifically looking whether it was possible to detect these 3 centimeter masers. Okay, so to assess the Lyman alpha pumping efficiency, we need to understand Lyman alpha scattering rate. And this is something we start to understand better and better. So when you want to compute the Lyman alpha scattering rate, you need to know the production rate of Lyman alpha, so how many photons are inserted per unit volume. You also need to know how many times a photon scatters prior to escape, and the product just gives you the scattering rate. Right, so for example, if you have an optically thick medium, we know how many times a photon scatters before it escapes. And it turns out that the number of times a photon scatters is roughly the line center optical depth of the scattering medium. So to give you a sense for the magnitude of this number, if you have a static sphere, say, with a column density of 10 to the 20, well, the shape doesn't matter, then the line center optical depth is 10 to the 7. So photons would scatter 10 million times on average before escaping from such a sphere. Okay. Now, why is this relevant can this be relevant for the direct collapse black hole scenario? So I've copied here a sentence from a paper that Avi wrote 12 years ago with Volker Brom. So if you have atomically cooling dark matter halos, Avi wrote, a central condensation consisting of 1 or 2 clumps that contain 10% of the total baryonic mass of the galaxy. Now, as long as H2 formation is suppressed, these clumps can basically collapse uninhibited without fragmenting and possibly directly into a black hole. So this scenario where you have the gas cloud collapsing straight into a compact massive black hole without forming any intermediate stars or any intermediate star formation is what is referred to as the direct collapse black hole scenario. And this is something that people have been working on quite a lot in the past few years. So this image here is is made by John Wise. So this is a simulation that this group did and sort of representing, it's a snapshot in their simulation in a scenario where where the direct collapse black hole scenario is thought to be happening. Now, okay, so you may wonder, it's actually quite unusual for H2 formation to be suppressed. And you can actually achieve this by bathing your gas cloud or the gas cloud that you see here in a very strong Lyman-Werner background. And you can actually show that this can happen in these conditions can occur in the very early universe. So it's possible for this direct collapse black hole scenario to take place. And of course, this scenario has been invoked to explain the existence of supermassive black holes as early as redshift 7. It's a very complicated problem, and at this stage, I think there's a lot we don't understand about it. So I think it's very useful to have an observational signature of the process, right? Now, one way you can summarize the requirements for direct collapse black hole scenario are that you require isothermal collapse at 10 to the 4 Kelvin, and gas needs to be pristine and free of H2. Now, all these conditions are relevant. 10 to the 4 Kelvin implies that you have production of Lyman alpha, right? You cool by Lyman alpha emission, basically. And in addition, at 10 to the 4 Kelvin, or like temperature slightly below that, the gas is highly neutral. So if the gas is highly neutral, it becomes very easy to build up a large column density of H1. And as I mentioned earlier, if you crank up your column density, you crank up the scattering rate of your Lyman alpha photons proportionally. Right? So, right. In addition, the condition of pristine gas and free of molecular hydrogen is also important. Because whenever we study Lyman alpha transfer in other environments, Lyman alpha transfer is often very much affected by processes that destroy it. For example, dust. Dust generally kills a significant fraction of Lyman alpha flux in galaxies at lower redshift, or most redshifts. Now, in this pristine gas, there is no dust, so this mechanism is irrelevant. There's another interesting mechanism that molecular hydrogen in one of the excited vibrational states has transitions close to Lyman alpha. This can absorb, these molecules can absorb Lyman alpha and then re-emit it at different wavelengths, so effectively destroying Lyman alpha. But again, direct collapse black hole scenario, there is no H2, so this mechanism is basically, or at least very little. This mechanism is not operating. Now there's other processes that can kill Lyman alpha, and that is H- can absorb Lyman alpha photons. In addition, a photon in the 2p state, an atom in the 2p state can collide with a proton which can put it in the 2s state, again effectively destroying the photon. But you can actually show that in the conditions that we see for these direct collapse black hole scenarios, this is not efficient enough to kill off or to reduce the scattering rate sufficiently for what I'm going to show next. So it is interesting that the direct collapse black hole scenario, if you look at the key requirements for this process to happen, are actually identical to the key requirements for optimal Lyman alpha pumping. Right? So for this reason, we started looking at whether, if there's any detectable signature of, perhaps in these fine structure lines of this process. So with Shiv Sethi, we set out to study Lyman alpha transfer in simplified representations of this scenario. And we looked at spherical clouds. And the only reason for doing that is that Lyman alpha transfer is a complicated process, but at least in this geometry, we have analytic solutions and we can treat this problem accurately. Right? So it will be interesting just to see what these kind of calculations give us. So to give you some results, not going to go into all the lines. This is showing the number density of hydrogen atoms in the 2p state in blue and 2s in red. Right? And the lower panel I've eliminated. Now, the main point of this figure is to show that indeed the 2p level is overpopulated compared to 2s. So we have negative optical depth through the fine structure lines. Right? And just to go back to this picture, negative optical depth meaning to CMB photons that would be passing through the cloud. Right? Now, what does it mean for the optical depth? So we've calculated that. So I'm showing here the optical depth as a function of cloud number density, or mean cloud number density. Now, the y-axis is top secret until the next slide. But what I'm going to show you is, what I wanted to tell you first is that when the optical depth is negative, the simplest way to interpret this result is to say that the background CMB is amplified by e to the power, the absolute value of your optical depth. Right? So this is the numbers. So we get values up to -30, -40. Right? So just, this would naively imply a boost by a factor of 10 to the 10 to the 10 to the 20 of the background CMB. Now this boost is not achieved in reality. For boosts larger than 10 to the 5, the CMB starts affecting the level populations. So we get a MESA saturation at a at a magnification factor of 10 to the 5. So what would this look like in terms of spectrum? So I'm showing here a redshifted spectrum for hypothetical direct collapse black hole scenario at redshift 10. So it redshifts down to 900 megahertz observers frame. And the structure you see in the line is real, and it's due to the hyperfine structure inside the fine structure line. Right? So the structure that you see in these lines is entirely due to atomic physics, and this would be robust against like any complicated gas dynamics that is going on inside the cloud. So this kind of signature is a robust prediction. So the 3 lines here corresponds to different line center optical depth to this fine structure emission. And I just want to stress that the case, our fiducial case that I showed you before, corresponds to tau naught is -40, so that will be the red dashed line. So it would be a line that is about 30 angstrom, 30 megahertz wide, serves a brightness temperature of 10 to the 5 Kelvin, a few by 10 to the 5 Kelvin. Now, of course, this sounds exciting, and it is, but you have to realize that this comes from a very small part of the sky, right? These clouds are small and compact. So for the conditions that I was showing you, oh, right, there it is. The angular scale of these clouds would be only a few milliarc seconds. So, right, so you have a very bright point source, but the total flux in the source is small. Now, actually, just yesterday, I actually got an email from Shiv that, these are all very new results, right? So the signal corresponds to the flux that we predict is of the order of a few microjansky. And I'm not a radio astronomer, so that didn't mean much to me at all. So, but apparently, according to Shiv, like surveys with the SKA are proposed to go sub microjansky. So in principle, this could be detected by, well, if it exists, it could be detected by SKA, which is, to me, is just a bit ridiculous, that this possibility is there, because this is pristine gas, an atomically cooling halo, right? So the fact that it's even, it's worth discussing that we might be able to detect it with SKA, to me is very exciting. So I'll leave you with the conclusions and take questions.
Are there any analogous lasers of helium?
I have no idea. That's a good question. I mean, well, you would need to excite helium into the excited stage, which would require higher gas temperatures, right? So,
as far as I remember, the only fine structure line is
right, on the ground state, right.
Other questions from Mark?
Testing. did this before. Where's my mouse? I can't see my mouse. Command L.
Scroll on the side.
There we go. Thank you. You can just go to.
View? No. What do you do?
I think you can do the bottom right there.
Okay.
Yeah, that button there. One more. Thank you.
So, this mirroring is messed up. It will take longer.
Sorry.
Where are the preferences? No idea. So you tried this before, huh?
We need mirrored displays. Is what he did last time.
Let's try.
Okay, thank you. Okay. Well, thank you. It's good to be back. So the full title of this talk will be How Do Large Samples of Eclipsing Binaries, I'm talking about thousands of eclipsing binaries, tell us about the formation, environments, and evolution of massive binaries. So this is just going to be a hodgepodge of my thesis results in about 10 minutes. But one important update that's happened in the past 2 months, the birth of our son, Malachi Regulus Mo. He's about 2 weeks old now. I hope to get some sleep here soon. But the middle name, Regulus, is Alpha Leonis, meaning the heart of the lion. That was used by maritime navigators to guide their ships. But astrophysically speaking, it's a rapidly rotating B-type main sequence star. And we see the orbital reflex motion of the star. So we know there's a companion to Regulus. We just don't know what it is. And so there's two theories. One theory is that this star used to be a more massive star that has since evolved into a white dwarf, donating its material to Regulus. The other theory is that this is just a normal K-dwarf star, and that this star is rapidly rotating just because that's the natural evolution of these massive stars. So Regulus is just a nice mystery in our galactic backyard. But there are other astrophysical mysteries in terms of binary evolution. And so half of B-type and O-type main sequence stars will interact with a closely orbiting stellar companion. And they can evolve to produce a plethora of these astrophysical phenomena. So in order to understand the rates and properties of these kinds of systems, we better understand their progenitors. So, as of 2012, these were the best statistics we had on the closed binary properties of massive stars. First off, all of these spectroscopic binaries are in the Milky Way, so they have roughly solar abundances. Second, to measure the mass ratio, which I'm plotting on the y-axis, you have to see the combined spectrum of both stars. And since main sequence stars follow a very steep mass luminosity relation, you can only measure mass ratios and detect SB2s if the mass ratio is above 0.25. Now, more extreme mass ratio binaries may appear as single-line spectroscopic binaries, but we don't know if they're extreme mass ratio binaries or if they contain white dwarf companions, just like possibly like Regulus. And finally, you see as we go toward longer orbital periods, the sample size gets pretty poor, and you're affected by selection effects. So how can we probe lower metallicities, smaller mass ratios, and longer orbital periods? The fact that we have very poor statistics in these portions of the parameter space should incite immediate fear and concern. Fortunately, we recently celebrated the 50th anniversary of Dr. Strangelove. And Peter Sellers here helped me to learn how to stop worrying and love eclipsing binaries. And in particular, I have fallen in love with the Ogle data set. Ogle stared at the Magellanic Clouds for 7 years. They got 500 plus photometric measurements on 50 million stars, and they identified tens of thousands of eclipsing binaries, several thousand of which are these early type eclipsing binaries with B-type main sequence primaries. So my thesis was just mining this data set, seeing what we can learn from these eclipsing binaries. But there's some advantages of these data sets. One is the Magellanic Clouds have massive stars that are at lower metallicities. And so we compared the eclipsing binary properties of massive stars in the Milky Way and the Magellanic Clouds. And we don't find any variations in the binary properties. There's binary fraction, the period distribution, the mass ratio distribution. And so that's saying that massive binary formation is relatively insensitive to metallicity, at least on this metallicity range. Also, Ogle was sensitive to these shallow eclipses, so it could detect small, low mass, closely orbiting companions that pass in front of these B-type main sequence stars. Next, we have thousands of eclipsing binaries. So even though there's geometrical selection effects where you're less likely to see eclipsing binaries that are farther apart, we can still get decent sample statistics on these eclipsing binaries with intermediate orbital periods. And the coolest thing is that we know the distances to these eclipsing binaries in the Magellanic Clouds. And what this means is, along with the dust-reddening law and stellar evolutionary tracks, we can measure the physical properties of eclipsing binaries based solely on the photometric light curves. So the color gives us information on the dust extinction. The phase of the secondary eclipse tells us the eccentricity. The ratio of the eclipse depths tells us the luminosity contrast, and therefore the mass ratio. Again, since we know the distance, the brightness, the I-band magnitude, can be maps to the primary mass. And then here's the cool one. The sum of eclipse widths tell us the sum of the radii. And according to the stellar evolutionary tracks, we can infer an age to about 30%. So after running this pipeline on a bunch of systems, there's some cool trends that come out of the data. So here's comparing the dust extinction as a function of time. And you can see that these eclipsing binaries in young environments are embedded in these dustier environments. Older systems live in less attenuating environments. And so this is a nice empirical relation. If you're modeling the spectral energy distribution of distant galaxies, and you assume some kind of 3D dust geometry, you're going to recover the incorrect star formation history if you don't account for the fourth dimension, the fact that younger, systematically bluer populations will be more highly extinguished. Here's another trend that came out of the data of fitting about 130 eclipsing binaries in this orbital period range. First, we find that all these eclipsing binaries with young ages are born with large eccentricities, which was very surprising because we look at other systems and they're usually more circularized. And so this is telling us that these eclipsing binaries with intermediate orbital periods form via dynamical interactions, either tidal disk capture, three-body exchanges, or secular evolution via Koosai cycles. And also this slope in the eccentricity age relation gives a diagnostic for the tidal damping constant and these hot stars with radiative envelopes. We've been able to measure the tidal damping constant before, but that was for cooler stars with convective envelopes. This is the first measurement for these more massive stars. So out of the thousands of eclipsing binaries we looked at, we found 22 of these weird systems that, in addition to the eclipses, they showed this sinusoidal variation between the eclipses. And we realized this is irradiation effects, where the hot B-type main sequence star is heating the surface of the companion. In order to get reflection effects, the companion has to be comparable in size to the primary, but substantially cooler. And so we realized that the companion is a pre-main sequence star, a low-mass pre-main sequence star. And so this is, I mentioned the majority of these massive stars form in binaries. We've seen them where they're both pre-main sequence stars. We've seen them where they're both main sequence stars. But here we are able to find these systems in this unique phase of evolution where you have a pre-main sequence low-mass companion that's still contracting towards its main sequence phase, and the more massive star has already reached its main sequence phase of evolution. When we look at the positions of these 22 reflecting eclipsing binaries, we find that they're in typically in H2 regions. And so the blue dots are all the eclipsing binaries, B-type eclipsing binaries. You can see they follow the bar of the LMC, whereas the 22 reflecting systems with pre-main sequence companions typically reside in H2 regions. Not only that, the properties of the eclipsing binary is correlated with the type of H2 region in which it resides. For example, the youngest system we found, which has a large reflection effect amplitude, a deep eclipse, an estimated age of 0.6 million years, is in the bright Tarantula Nebula. We found another young system. As you can see, there's a little compact H2 region where that system resides. But older eclipsing binaries are these less, more diffuse H2 regions. So, last conclusion here. As my mom always told me, mind your P's and Q's. Well, I'm sure what she meant by that is to never assume that the distributions of period and mass ratios are uncorrelated. And so as of 2012, this was the parameter space of mass ratios and orbital periods that we could measure. And at the end of my thesis, as of now, we're filling in this parameter space with eclipsing binaries, long baseline interferometry, and Nancy Evans here is using Cepheus to measure the green parameter space here. But eclipsing binaries is able to show us that there are extreme mass ratio companions to those B-type main sequence stars. This is my last science slide. So we measure the binary properties for different masses and orbital periods. And we find that solar-type binaries have a roughly uniform mass ratio distribution. The red points up there. And they also exhibit this excess fraction of twins, this excess frequency of mass ratios very close to unity. Massive binaries are completely different. Although they show correlated components, correlated masses at short separations, indicating they co-evolved, as you go towards wider separations, the massive binaries favor more extreme mass ratios, indicating that the components formed more or less relatively independently. So, in just 3 bullet points, for my thesis, I used eclipsing binaries to probe the properties of massive binaries with low metallicities, extreme mass ratios, intermediate orbital periods. We developed this really cool pipeline where we could measure the ages of the eclipsing binaries, and they now serve as diagnostics for the evolution of H2 regions, dust extinction, tides. And we're finding more of these extreme mass ratio companions to massive stars than originally believed. And so there's some hints that there may be an order of magnitude or more of the type 1a progenitors and low mass X-ray binaries than previously predicted. Yes, so what we can say is that the average O-type star has 1.9 plus or minus 0.2 companions. And so when I show this diagram here, the binary fraction is essentially 100% by the time you get out here. And so all the systems, visually resolved binaries, and common proper motion pairs that you see, they're basically all tertiaries.
Looks like there are no more questions. So let's end all the speakers.
Yes. Just curious, you doing mass spectroscopy or new spectroscopy? I'm just curious about the design I distribution.
The V sign I distribution?
Yeah, how do they spin different in a single?
Yeah, so we're trying to get some follow-up spectroscopy on those very young reflectance systems. I haven't thought about taking a larger sample of V sign I. Yeah, but you can do it with a SQL effect. So the main, so one thing I want to try to do is get multi-epics to get binary mass orbits too. But yeah, a larger sample of V sign I. I do know that the European groups have done the O-type stars, hundreds of O-type stars. So
my interest is the hypervelocity stars right there, the V-type stars, and the ones we can measure, we can't measure low PSI. Ones where you have regular shell spectroscopy, they're typically gas rotators, which is what you expect, unless they came from the compact binaries, which is arguably should have come from. Theoretically, you think there should be slower rotators to type of synchronization anyway. That's what I was kind of curious about. Because all the classic papers are apt and whatnot, right? All steady, quote, single, V stars. Anyway, I'm just kind of curious what's binary.
So have you talked to Selma Deming?
Yes.
Oh, okay, yeah. So she has a theory that all these rapid rotators are post-binary evolution. So their mergers or stable mass transfer that spun it up.
Oh, for the O stars, yeah, that makes perfect sense. Your most massive O star is just the merger of two stars. It's not actually a single star, or it was one. Yeah.
But you can also have some kind of mass transfer and then a supernova that then ejects it, and so then you get the high velocity, but also the rapid
I thought
rotation.
Selma's conclusions were all O stars. I mean, that's really her focus.
Yeah, that's definitely, but some of that scales down to B-type stars. So.
Yeah, I care more about the 3 to 5 mass.
So late,
That's always the end.
Okay, so late B. Yeah, I don't know. I don't know if you can explain